Hello, everyone, and welcome back. My name is Mr. Kovalt, and in this problem, we're going to go over how to figure out if you have enough heat produced that's going to raise the temperature enough to melt iron. So let's get into this. So thermite reactions, thermite mixtures are used for certain types of welding. The thermite reaction is highly exothermic. Here is the form. Here's the reaction. Fe2O3 solid mixed with or reacts with aluminum. Solid is going to form aluminum oxide Al2O3 and liquid iron. This is highly exothermic. The delta H, the change in enthalpy, is negative 852 kilojoules per mole. Okay, so here we have 1 mole. They're giving us 1 mole of the Fe2O3 and 2 moles of aluminum. They're mixed together at room temperature, 25 degrees Celsius, and a reaction is initiated. The liberated heat is retained within the products, whose specific heat over a broad temperature range is about 0.8 joules per gram degree Celsius. The melting point of iron is 1530 degrees Celsius. Show that the quantity of heat liberated is sufficient to raise the temperature of the products to the melting point of iron. Okay, so what do? First thing we need to do is figure out if this is a limiting reagent problem or not. Remember, a dead giveaway for a limiting reagent problem is that they give you two amounts. They give you an amount of each of the reactants, but that's all they give you. They don't give you any other information. They don't tell you it reacts completely or that one side reacts completely over the other. So we have to figure that out. So notice here that the ratio of the reactants here is 1 to 2. So that means that for every 1 mole of Fe2O3, in order for this to react to completion, we need 2 moles of aluminum. So if we have 2 moles of aluminum, then all of the aluminum is going to react with all of the iron 3 oxide, and then we'll have nothing left. So in that case, there would be no limiting reagent. If we don't have enough aluminum, then the aluminum is going to run out first, and then so aluminum is going to be the limiting reagent. If we have too much aluminum, then we're going to have leftover aluminum, and the iron 3 oxide is going to run out first, and that'll be the limiting reagent. So let's look at the moles that we're given. We're given 1.00 moles of Fe2O3 and 2.00 moles of aluminum. Notice that the ratio here is exactly the same ratio here, which means that we have exactly the amount we need of the aluminum to react completely with all of the given Fe2O3. So that means that this is not a limiting reagent problem. That means we don't have a limiting reagent because both reactants are going to react completely and we're not going to have any left over. So that's great. We don't have to figure that out. So if we look at the ratio between the two reactants, we see that the mole ratio is exactly the same. In that case, everything completely reacts. And so we know that therefore, since all of this reacts, we're going to get the same amounts of moles here. So we're going to end up with 1 mole of Al2O3 and 2 moles of iron. But we can calculate it out and show that as well. So I'm going to start with 1 mole of the Fe2O3. So we have 1.00 moles of Fe2O3. And then we use the mole ratio, so it's 1 to 1 for the aluminum Al2O3, the aluminum oxide. So we have 1 mole of Fe2O3 on the bottom, 1 mole of the Al2O3 on top. So moles cancel out, and then we can calculate the gram. So using the molar mass of the aluminum Al2O3 aluminum oxide, we got to calculate that. So the molar mass is going to be 101, 9622. So that's going to be 101, 9622 grams of the Al2O3. And then that's going to be 1 mole of the Al2O3 on the bottom. So moles of the Al2 cancel out, Al2O3. And then all we need to do is multiply across the top and the bottom, and that's going to give us 101, 92. Oops. Since they're all ones, it's going to be 101.9622 grams of the Al2O3. And we could do the same calculation starting with 1 mole of the Fe2O3 and seeing what the grams, what the mass of the iron is. So let's go ahead and do that. And just by the way, the reason we're doing this is because we need to get the total mass of the products. Because remember, we are told that all of the heat, the liberated heat, is retained in the products. And we're going to have to use Q equals MCAT here to find the final temperature. So we're going to need the mass of the total products formed. So here we know that 1 mole and 2 moles of iron is going to be formed. So we could just take 2 times the mass of the iron, but we could do stoichiometry just to show that that's what we're going to get. So we're going to start with 1 mole of Fe2O3. And we're going to use the mole ratio to go from 1 mole of Fe2O3 to 2 moles of the iron. So then it'd be, 1 mole of the Fe2O3 on the bottom, 2 moles of iron. So moles of the Fe2O3 cancel out. We have our 2 there. So now we look up the molar mass of iron, 55,845. So 55.845 grams of iron for every 1 mole of iron. So moles of iron cancel out. So now all we need to do is multiply across top, divide by the bottom. And again, we get 2 times the molar mass, which again gives us 111.69. 111.69 grams of iron. And so these 2 together added up is going to give us the total mass of our products. So adding these up together, we get 213.6522. So 213.6522. Now, as far as sig figs go, here we have 3 sig figs. So when you multiply and divide, your final answer should have the same number of sig figs as the least number. So the least number is 3 here. So that means 1, 2, 3. So we're going to underline the 1 here. So that tells us that's our last sig fig. But we're going to keep the rest just to avoid rounding errors. Same thing here. We have 3 sig figs here. That's the least number. So again, 1, 2, 3, underline the 1 there. We'll keep the rest. So when you add the numbers together, remember when you add, the rule is that your answer should have the same number of decimal places as the least number. Since our last significant figure is the ones place here and the ones place there, they're both the same. So the least number of sig figs stops at the ones place. So we'll underline the 3 there since that's in the ones place. We'll keep the rest to avoid rounding errors. So this here is grams. So that's the total number of grams, the mass of the products formed. And again, as we said, all of the heat liberated in the reaction is going to be absorbed by the products. Okay, so now we can use our Q equals MCAT. So Q, now we're told that the delta H of this reaction is negative 852 kilojoules. So let me write the equation. So the Q equals the mass times the specific heat times the change in temperature. Here we're talking about the products, so I'll put P for products. So what is the heat that was absorbed by the products? Well, that's the heat that was released by this reaction. We're told that this is negative 852 kilojoules per mole, right? So here we have 1 mole here. So that is going to be the amount of energy that is released. Now, since we happen to have the exact same ratio between the Fe2O3 and the aluminum as we have in this formula, then that means that these two reacted are going to produce that amount of energy. So again, this is exothermic because it's negative. That means that the reaction releases this amount of energy. That means that this is the energy absorbed by the products. So if you remember, Q of 1, right? So in this case, Q of the reaction is going to be equal to Q of the products, meaning that the heat absorbed by the products is equal to the heat released by the reaction, except this is going to be negative because negative means release, and these got to be opposite, equal but opposite. So that means that if I put in negative 852, so that's going to be negative 852 kilojoules is going to be equal to positive, because, right, this is going to be positive 852 kilojoules. So the amount of heat absorbed is the same. So the heat absorbed by the products is positive 852 kilojoules, which is going to be equal to 852,000 joules, right? And we get that by the conversion factor. So I have 852 kilojoules over 1. I know that 1 kilojoule is equal to 1,000 joules. That's what kilo means, 1,000. So 1 kilojoule on the bottom, 1,000 joules on top. Kilojoules cancel out. So 852 times 1,000 gives me 852,000 joules. So why is it important to put in joules? Because we have specific heat here, and specific heat is given in the unit of joules, right? So you notice here we have joules there, so we want to make sure that the heat absorbed is in joules. Okay, so now that we got all of this out of the way, let me erase this to give room, right? I don't want to erase that, that's my mass. Okay, so here, oops. So what's Q absorbed by the products? 852. So we're going to write 852,000 joules of energy absorbed by the products. That's going to be equal to the mass. This is our total mass of the products. So that's going to be 213.6522 grams. Again, I'm going to put a line underneath the 3. That tells me that the last sig fig in this measurement is the 3. And again, since this is 3 sig figs from before, the last sig fig for here ends at the 2. And then the specific heat is 0.8 joules per gram degrees Celsius. And that's equal to the temperature change. But remember, temperature change is equal to final temperature minus the initial temperature. So we're going to subtract that in. We're going to substitute that in for this. So then we're going to have final temperature minus the initial temperature, which we're told is, where is it? 25 degrees. There it is, 25 degrees Celsius. So that's going to be 25 degrees Celsius. Let me make sure that's correct. That is correct. Okay, so now that I have this set up, the grams here are going to cancel out. So then I'm going to multiply these two together. When I multiply those together, I get 179.22. So this is going to be equal, so this is 852 joules equal to, and I get 170,922. And that's going to be joules over degrees Celsius because the grams cancel out and I have joules over degrees Celsius. Okay, and then this is going to be multiplied by TF minus 25 degrees Celsius. So now what I'm going to do is I'm going to multiply this and distribute this to these two terms here. So I'm going to multiply 170,922 to the TF and to the minus 25. When I do that, I get, again, 852,000 joules multiplied by, it's going to be 170,922 joules per degree Celsius times TF, and then minus, and now I'm going to multiply this times the 25, and there I get sorry, that's a mistake. This is not a comma, that's a period. I misread my own writing, which makes sense because this times 0.8 should not give you something that huge. Okay, now that looks better. So then this times 25, that's going to give me, what was that again? 4273. So 4273.044 joules. Yes. Okay, much better. Okay, so here I have joules. Here I have joules over degrees Celsius. Here I have joules. So now that I have joules over here, I'm going to combine like terms. I need to get like terms together. So that means I'm going to erase all of this because I don't need this. Get this out of the way. So I have going to add 4,273.044 joules. Okay. And oh, by the way, let's take care of sig figs here. So I'm multiplying. So remember the sig figs here should be this. The answer here should have the same number of sig figs as the least number here. So here I have 3. Here I have 1. So that means this is my 1 sig fig there. So I'm going to underline that. And so it's going to be here as well. So again, the sig figs is 1. So then this is going to be 1 sig fig there, 1 there. So now I'm going to add on this side a positive 4,273.044 joules. And when I add these together, remember when we're talking about sig figs again, adding and subtracting has a different rule. So here the rule is that the when you're adding and subtracting, the rule is that your answer should have the same number as the least number of decimal places. Or another way to put it is um, the least precise measure, or the one where the last significant digit is the farthest over this way. Um, so notice that this one has the significance in the thousandths place, and this one has the last one in the thousandths place. So that means the answer here also is going to have the last significant digit in the thousandths place, because that's the least precise of both of them. So I'm going to add these together, and when I do that, I get 856,273. So 856 273. I'm going to leave off this because I've got a lot of digits already. That's going to be in joules, and that's equal to 170.922 joules per degree Celsius multiplied by the final temperature. Now I can just divide both sides by this, get the final temperature by itself, TF, 170.922 joules per degree Celsius. Divide that over here, 170.922 joules per degree Celsius. This is going to cancel out. I'm left with TF. So notice here that joules are going to cancel out, leaving me with a temperature unit, degrees Celsius. So, which is what I would expect if I'm finding final temperature. When I divide these, I get 5,009. So TF is equal to 5,009 0.7 degrees Celsius. And again, since I'm only allowed up to the thousandths place for a digit, so again, rounded, that would be 5,000 degrees Celsius. And so the question is again, show that the quantity of heat liberated is sufficient to raise the temperature of the products to the melting point of iron. The melting point of iron is 1530. We have enough heat to raise the temperature of the products to 5,000 degrees Celsius, well above the melting point of iron. So this is going to produce a liquid iron. And that is the thermite reaction. And I hope this was helpful. This is how you can use your calorimetry, understanding of calorimetry, and the Q equals MCAT equation to help you solve problems. I hope this was helpful. If it was helpful, by all means, like the video, share the video, hit the like button somewhere over here. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with, or a topic you would like me to cover, put that down below. I would like to do that for you. Thanks for joining me, and have a great day.